about the shock diffraction by convex colored wedges. This work is collaborated with in Oxford. So first, at the beginning of our talk, I would like to show an example. I think you all are experts, so I think I skip this example. This is a very famous example. So you see the white cloud is kind of shockwave. It's called sound barrier. Okay, so now directly go to our problem. Our problem is work on shock diffraction. Shock diffraction is that the incident shock passes the wedge from left to right, and the wedge is stepped down. Compared to shock reflection, it's stepped up. So I first draw a picture to compare these two structures. So for shock reflection is that the wedge goes up, and we think about this is shock reflection for SR, and shock diffraction is that the wedge is going down. So we call it shock diffraction. And so initially there are two constant states. You see, we call it Riemann data. So the left-hand side is U1, right-hand side is U0. So what happens when the incident shock after passing through the wedge? So which model we will use and which method we will use to solve it? So first is the model. The model we use is the potential flow. Potential flow is actually from the Euler system, but the flow is rotational. So we have the first one is conservation of mass, and the second one is Bernoulli law. Bernoulli law is come from the conservation of momentum. And now, if we can replace the density rho by the velocity potential, phi is the velocity potential. So I should say that the velocity u is actually the gradient of the velocity potential for the elasticity. And then we plug in, and this becomes to a second order wave equation. It's called the potential flow equations. And this equation have a long history. I think it's a fundamental PDEs in aerodynamics, also in gas dynamics. And Adama studied this long time ago, 100 years ago. And Morawitz also used the potential flow to study the shock reflection problem. And they got some local results away from the, I think from the degenerative lines. They got some result about that. She got some result about that. And also Maeda and Thomas studied the local existence of shock wave in 1978 by potential flow equations. And
sorry, what is this for equivalently? How you get this equation from the other?
You see which one? Which equation? For which equation? This one?
These two equations are equivalent to the system?
Yeah, equal to the Euler system. You want to show how to derive this one from the Euler system?
No.
Oh, from this one, you see this?
Two, how you get it?
From this two, got the wave equation. This just plug in, you see rho. First, you have Bernoulli, so you can get rho. The density is just a function of the potential, velocity potential for this one. You can really get, and then plug in to the conservation mass, you got the second order wave equations. It's called the potential equations. Okay. And this
in the parentheses, it's the function of these things.
Yeah, it's an algebraic.
No, the second line.
Yeah, this is an algebraic.
Okay,
it's a good question. So maybe I should slow down and take more. But I think all you are experts about that, so I plan to skip it. So recently there is a breakthrough. I call it breakthrough is by Michel Friedman and Fukuicha and also Min Jin, and they are working on shock reflection problems by the potential flow equation. They got the global existence result for if the wedge angle is large enough near the half pi in actually this work is done in 2005 or 2006, and then after 4 years, finally published in Annals in 2010. And after that, recently they are writing a book, and as far as those now it's 600 pages, and they've gotten that this structure, the regular reflection, actually up to detach angle. Yeah. So And at the same time, the Pei and Guichan and also Friedman got that the regularity. Also, I will show next page maybe. So the regularity of these problems when the solution across the solid arc or the degenerate line. So this actually got the regularity should be C11. So and also Dennis Sears work on the Chambly-Jin gas, the gamma equal to -1 for about this problem in 2009. So there are many results about the shock reflection now, but there's no certainly I think very few results about shock diffractions. Because our problem involves shock wave, so now I give a quick introduction about shock wave. Shock wave is actually the weak solution is piecewise smooth. You see, both there is a discontinuity lines, and apart from the continuous line, in each domain, it should be smooth solutions. First, we define that this is kind of weak solution. So we define the solution in weak sense, in the distribution sense, that there's a text function side, ellipse function, then they should hold for any text functions with compact support. So this is defined in distribution sense, and U0 is the initial data. And now we can integrate by part to get that if this solution is piecewise smooth, so the only jump is along the discontinuity line. In each domain, the solution should satisfy the equation. Now it's a general equation. It satisfies the equation classically. And along the discontinuity line, we can integrate per part and get that actually this must satisfy the Rakin-Equal condition. Is that the jump of the solution and also flux dot the normal direction should equal to 0 is actually something like conservation. From the physical meaning, you can think about philosophy is conservation of certain quantities. So we also know there's no uniqueness about the weak solution, so we impose entropy condition. Entropy can come from this one. This is general one. Eta is something like the entropy. If the system have entropy, we know that there's some discontinuity. This is kind of second kind of thermal theory that the entropy should increase in any case. And for our problem, for the potential flow, actually this density will increase when across the shock from in the pseudo speed, in the pseudo direction, the density should increase. Now, okay, after introduction shock wave, now we are focused on the shock diffraction problems. As we know, the initial data is actually invariant under stretching of space coordinate because it's constant, so it's invariant when you're stretching in this direction. And also the equation is invariant if we do a change of coordinate. So we will go to find the self-similar solutions. Is that the solution in the following way? We define psi is x over t, eta is y over t. It's called actually called the pseudo coordinate. So after that, we can write the equation again to the second order. Actually now it's mixed type equation. It's just in psi eta coordinate. Now we find that the equation is elliptic if the gradient of the velocity, gradient of the velocity potential is a velocity should smaller than some certain number. Here is also involved on the potential function itself. And the solution is supersonic. We call it hyperbolic equations if we satisfy this one. So before we solve it, we don't know which part is elliptic, which part is hyperbolic. So if this equal, it's sonic line. We call it sonic line. It's a mixed type. So, okay. So now is the structure of shock diffraction problems. Is that the shock will interact the sonic arc. Sonic arc is where the gradient phi is equal to the right-hand side. So it's actually change the type. Outside is supersonic. Inside should be elliptic. After solve, we will prove that it's elliptic. And become a transonic shock. And the sonic circle C0, it divides the region into two subregions. The outside is supersonic, inside is elliptic. And so our problem is become to find the position of a transonic shock and also solve the equation in the subsonic domain. And prove that actually inside is elliptic. So, okay, this problem gives some history. This problem is studied by Lighthill, and also I think proposed these papers, and 1949 same papers, I must say. Actually, Lighthill studied the problem when the angle is small. This one is a perturbation about this wedge angle. So he got some use the particular and get some the structure of shock is actually in this way. So we also call this problem a Lighthill problem. Studying it's a British mathematician in 1949, 1950. It's by asymptotic analysis, and also some physical result in this at the same time. But as far as I know, after that, almost half century, there's no result for potential flow equations. Only result is on the simpler model, is a nonlinear wave system. This model is, I think, somehow related to the unstable UTSD equations similar. So for that model, simpler model, King in 2010 got that result for right wedge angle, and one additional assumption that the shock should have strength at the point. So then she can use the perturbation method to get that the solution actually exists. And after that, we remove this assumption and prove that for any wedge angle actually, because then for nonlinear system it's very easy. Actually, there's no another kind of sonic arc, so it's very easy to get that for any wedge angle. We can get the existence. But for potential flow theory, it's another story, actually. Because the angle compared to this shock reflection, with the shock reflection, the angle is less than pi. So we can get the existence very easily by near the corner by the general ellipse theory. But for this one, it's bigger than pi, so there are no general ellipse theories. So the angle exterior to the wedge angle is larger than pi. So you can easily find a singularity, find a counterexample that actually for Laplacian equation, actually if for Dirichlet boundary condition, if the both sides vanish, and you can get a C1 alpha solution, alpha smaller than 1. But we know for potential flow equation, actually depends on the derivatives of the solution. So you cannot get it if the solution in C alpha smaller than 1 should get something alpha bigger than 1. So that's why there's no global mathematical result available for the potential flow. And also, Finn in 1959 showed that the convexity is necessary and sufficient condition for the solvability of Dirichlet problem for the minimal surface equation. You can write this sentence in Gerbach-Trudinger's book, and I think in chapter 12, chapter 13. And also, this kind of minimal surface equation actually is also a kind of second order empty equations, also mixed, not mixed type, is degenerate. And so for that is also you can calculate for Dirichlet problem. It's also no general theories. That's why Gerbach writes that in sentence say that's why we work on convex domain, not on unconvex domain. Yeah. So, but for potential flow equation, actually the boundary condition is very good. So we can hope to get additional regularity after that. So the result we got is that if for Riemann data U0 is smaller than C1, C0 means that at this point it's elliptic, no reflection wave. And also, if theta c is a critical angle, I will introduce in the next slides, that for any wedge angle between the critical angle and pi, wedge angle is mean that one. So there exists a global self-stable solutions in the following way. And also the solutions have good regularity, C1 alpha near the corner. And also outside is constant. And the transonic shock, maybe I draw a picture about the shock reflection. What is shock reflection is that the structure is that, okay, this is sonic arc and this is shock. The sonic arc we call C0. And so the transonic shock lies between two sonic circles. It's the left-hand side and right-hand side. C1 is C1. Between these two, so it's transonic shock, and it's C infinite except P1, this point. This point should be C2, because from the optimal regularity done before. And also the solution is stable when the wedge angle theta pi, theta w goes to pi. Yes. So now is the critical angle. I say theta belongs to theta c and pi. So the critical angle is that defined by the initial data. If we have initial data C0 and C1 on left-hand side, right-hand side, then this solid angle is determined by the left-hand side is that with the center and C0, the speed, and the radius C0 and the C1 is defined by the right-hand side. And then for potential flow, it's very interesting that these two solid circles sometimes should intersect with each other. And for potential flow, we carefully calculate from that if the gamma smaller than 3, it's indeed will intersect. And if this intersect, so this wedge angle who penetrates this intersection point, we call its angle is theta c is a critical angle. So for any wedge between this angle and pi, we can prove the existence. Because after this wedge angle, you find that the shock cannot survive between these two solid atoms because at this point it intersect. So should something happen? We don't know. And we check the experimental result. Maybe it happened by the Mach reflection configuration. Or maybe today I think about maybe it's disappeared. I don't know. Maybe something happens. So
numerical pictures?
This is from the numerical pictures. If had something, and then I didn't see because many possibles. So many possibilities. I don't know which should be after that. So it's very interesting after that. And
It's a shock at that point 0.
uh, you say which
Yeah,
one?
2 sonic.
You say yeah, if possibly. Yeah.
Possible.
Possibly. So we don't know.
They don't yet.
Yes, anything is possible. So
Sorry, could you just say again clearly so this one of these is sonic circle with respect to the state behind the shock, and the other or something. So how exactly
yeah.
are you defining these sonic circles again?
yeah, the sonic circle is this one is divided by a state behind the shock.
C0 is with
C0.
respect to the state behind.
Yeah, behind the shock. And C1 is ahead of the shock.
Yeah.
You say yeah. C1 is actually determined by because you can see the center is there and the wedge corner, and the radius is C1, so it's ahead of the shock. So it's actually transonic shock.
So, I mean, the C1 would be circular, centered at the wedge.
Yeah, wedge corner,
Right.
and the Z1 is here, so it's something the intersection.
Right, that's vectored in
This
this
is different from the nonlinear wave system, also UTCC, because they have to have a different center. Yeah. So that's why we have some another phenomenon consist to the physical example. You see physical experiment result. Actually, there's some insistence to that. It's very interesting about that. So now, it's because it's mathematical, so there's some difficulties in mathematical way. First, of course, is degenerate elliptic and free boundary. You also mentioned about about the free boundary difficulty come from free boundaries. I skipped that. So about the another difficulties compared to another problem is first is the gradual estimate. So is that the point? We need some estimate. So our way is that we actually develop the existence by solving another problems. That problem is finally we should prove that problem, the solution is actually the solution for the original problems. We use that way to get so we prove that existence for higher regularity around the corner. So we developed a new method for that. And for that method, we also should care about the boundary conditions because the rocking nuclear condition, as I mentioned, is nonlinear. The shock is nonlinear because of rocking nuclear conditions. So for our problem, we should take derivative along the shock wave. So, but mathematically, we should modification the rocking nuclear condition maybe near the something like near the background solution. And so you mean that different modification, because take derivatives means different boundary condition. So we should to design a new way to do that around the free boundary, especially away from the constant background. And also this one for the Mach reflection. So that's why, and we need to do more about that. So, okay. So our procedure is that first we think about the almost flat case. In that case, we can use constant as a background solution because the left hand side. So if the wedge is almost flat, we can expect that the solution is close to the state behind the shock. Should be that one. Also, light here do that way. Yeah. So we prove that, for that programs, we actually have better properties. All the solutions should satisfy all properties in cell 1. And also this velocity is close to the background solution near the shock. It's very important. We can get that the velocity, actually the smaller tone, the weight, actually velocity around the shock, so we can get many properties. And also they have some sign of the velocity. So v is negative actually in this domain. So the shock can only go this way, some like cone condition. So this property actually hint us to define the admissible solution for smaller wedge angle. So for smaller wedge angle, because it's too long, so I think it's better to skip it, the definition. After, if that, it will be several pages and waste time. And also, we use degree theory to prove the existence based on your book. The degree theory too. So the degree theory, we need to define the interaction set. Interaction set actually hinted by the definition of admissible solution. Admissible solution actually, the solution is that the shock should satisfy after the apart from the existence. So they show some additional nonlinear properties and to state this configuration nice. And also mainly uniform estimate and also modification of rocking unit condition for larger region and smaller region actually. So actually I should mention that recently I work with Misha and Richard prove that actually this shock is strictly convex. So means that this shock have better properties, strictly convex. And also, yeah, so maybe have better properties after that. After we have this property, we have got a better result. Okay, so because time is run out, I quickly to scale our result for just for the simpler case, the almost flat wedge. Almost flat wedge because we can use the constant as a background solution. So the Helline's property, we don't need modification, the rocking your condition around shock. And also we don't need to do many things about inside the uniform estimate about the solutions. We just got that. So we first introduce edge cutoff. And before edge cutoff that make that the solution is elliptic, especially near the solid arc, where the equation will change type. And then also boundary conditions for W. W is some special velocity in some way. And that we introduce that for that, then we can get an equivalent system that we will solve first. For that one, we should prove the local existence near the wedge angle, and also near wedge angle corner, and also prove the existence by Navier-Stokes fixed point. After that, we should prove that the solution we got is actually equivalent to the original. It should satisfy the original system. So by that, after epsilon goes to 0, so we prove some uniform estimate near the, especially near the sonic arc. We use sonic arc and the additional property makes that at this corner the velocity is actually equal to 0. So have better properties. That's why we can kind of say one alpha regularity. So from sonic arc, it's like sometimes the mixed type, the nonlinearity and also the degeneracy actually very good for the existence of regularities. We got some uniform estimate. To get after epsilon goes to 0, we got the existence. And then we can of course prove the equivalence of deduced set equation and original equation. And then for that one, smallness, we can get actually when theta W goes to pi, the solution goes to the original one. So it's stable with the wedge angle. And also we remove the degenerate edge cutoff in this case. So I think the final result, final remark is about what happens. Right? Also very interesting about that. When the theta c smaller, or the wedge angle smaller than theta c, as I said, if the gamma smaller than 3, this will indeed happen. Definitely will happen. So what happens about that? There should be marked reflection like this, or the disappear of the shock. So maybe some numerical analysis about that first, and what will happen is very interesting. And so Okay, so maybe I stop here and just thank you for your attention.
So for weak shocks, what's this critical angle do when the instant shock is very weak? Is it still there? Or
Yes,
is it-
still there. This not depend on shock. It depends on two sonic arc.
Right, but those will depend on the strength of the shock,
Yeah.
right?
You can see if that become very close to each other, so something become here, I think. So very large. Actually, this is very large. The quick angle will become very large. You can see this one. Oh, yeah, I think, maybe goes to, you see, you can see it become larger. This region will become larger.
Right.
So
they'll
something like
move
that.
together.
Yeah, something like here, just a very small wedge.
So does theta c go to 0 or something? What
Yeah.
happens?
I think should be. I don't know. They think about it before, so I just think maybe after that. But it should be. They can see very weak.
I don't understand how you can use potential flow when this shock strength is varying.
Yeah.
It's only homotropic and pop. So you don't have potential when the shock
Yeah, of course, after shock. But if the shock is weak,
It
so
is very, well, in that case, those circles are nearly on top of each other, right? And all this is happening in a very thin region.
you say this is, yeah, of course, this is the only region we can use potential flow. But you know, because what we care is about the shape of the shock actually. We see if for most cases, you find that the shape actually is coincide with the experimental result.
I
It's
can
also
believe
similar.
that's for very weak shocks.
Yeah, of course.
So
Yes, some shock may be.
in which case your circles should be nearly on top of each other. You've drawn them quite separate, which would be for a strong shock.
Yeah.
So I don't like this picture very much.
Yeah, you want
But
to
it might
formalize
also
it.
be true that the entropy jump is smaller in some regions than others. How do you think the entropy jump varies as you
The
come
entropy.
down through this?
Yes, across the. That's why the radius should smaller than this one, because the entropy.
As you come down your shock path, how
Yeah.
do you think the entropy jump is changing?
From right hand side to left hand side, this is pseudo direction. Yeah, this is should increase.
The
Yeah.
jump should decrease as you come
I
down?
think so. The shock
Yes,
is going to get
because
weaker.
this,
Yeah,
the jump will decrease, of course.
So your model will only be accurate at the bottom left-hand side.
Yeah, but of course, this proof we can prove that things still survive. Yeah, this is mathematical theory, so maybe.
I'm sure it would be nice to do it for Euler.
Yeah, of course, for light bit.
Well, you might, if you're just a transonic, so it's just slightly greater than Mach 1, you should be able to do some analysis in a thin region around this Mach circle. And it might make it simpler, actually. It's more or less moving with the sound speed. It's somewhat similar when you do the nearly zero wedge, you are making it even weaker.
Yeah, we can do this, of course. It's also in our that.
Well, not to plug my own work, but I mean, that's basically, I did that, problem like this with Joe Keller actually as part of my thesis, is exactly doing the local expansion around the wavefront. So that's where you get a Berger's equation.
Yes, that's
Yeah.
So that
exactly.
you can exactly do all the matched asymptotics in the weak shock limit here.
And you did have a small entropy jump.
Well, of course,
Of course, for
in the
weak shock, yeah.
weak shock, that's all third order, so it's,
But it was still getting less and less as you come
right, and you can compute
Yeah.
explicitly what the shock strength is.
Yeah, it's because, yeah.
Of course, that's a formal asymptotic construction.
If it was you and Joe, it's probably.
And also it's diffraction.
Also Mach reflection that may change.
Not Mach reflection. So the original thing that I did with Joe was weak shock. Was basically constructing. Lightail did the linear theory, and then we did all the nonlinear theory near the wavefronts.
Right.
But that's where you can handle things in a one-dimensional way.
Yes.
As long as everything is basically radial, then it's that breaks down Mach reflection. You get singular rays here too as well, where the shock. I mean, exactly the picture I showed in my talk, where the shock diffracts round.
Yeah.
Yeah.
Same thing.
Sorry, your talk so theta is always positive?
Theta. It's
I mean,
theta.
Wedge angle.
Or if it's positive, it's shock reflection.
if it's zero, I mean theoretical, let's say.
We cannot, because we have the critic angle. So after that, we don't know anything. So it's just before that. Yeah, it's very interesting. Maybe mathematically, maybe the short teacher.
No,
Any
mathematically, maybe the equations get something crazy, but simplified.
for that equation, we cannot use potential fluctuation because of Mach reflection. We cannot use potential fluctuation. We should use formula, so it become very. The formulas is different story. Even we don't know anything.
Some symmetries or something.
No symmetry. Just nonlinearity, and also transport. Quite difficult. Yeah.